to Into the Core, an in-depth exploration of Windows 10 IoT Core in South Seas IJ with Paul Sabanal. Before we begin, a few brief notes. Stop by the business hall located in Bayside AB during the day and for the welcome reception from 5:30 to 7 p.m. tonight. The Black Hat Arsenal is on in the Palm Foyer on level 3. Join us for the Pony Awards in Mandalay Bay BCD at 6:30 p.m. And finally, thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while we wait for your voicemail to pick up. With that, please welcome Paul.
Good afternoon. Thank you all for coming. I am Paul Sabanal, and I'm a security researcher with IBM Security's X-Force Advanced Research Team. And today I'm going to be talking about Microsoft's operating system for the Internet of Things called Windows 10 IoT Core. Okay, so here's the agenda for today's talk. First, I will start with an overview of Windows 10 IoT. Then we'll look a bit into internals and the security features, some mitigations that were implemented on the operating system, followed by a discussion on the attack surface exposed on a device running Windows 10 IoT Core. I will then talk about some tips and techniques in hacking a Windows IoT device, like static and dynamic reversing. Lastly, I'm going to give some recommendations on how to minimize the impact of the attack surfaces that we are going to discuss today. And after that, I'll wrap up the talk. So Windows 10 IoT Core is part of the Windows 10 Cone platform and is designed specifically for small footprint and low-cost, low-power devices. There are 3 editions of Windows 10 IoT, but we are only concerned with the Windows 10 IoT Core edition. That's for low-cost, low-power devices, and aimed at like smart home devices, IoT gateways, and digital signage. The other 2 editions are Windows 10 IoT Enterprise, which is it's actually the same with the desktop Enterprise, Windows 10 Enterprise, and it can handle the Universal Windows Platform apps and Win32 apps. And it's aimed mostly at kiosk, point-of-sale systems, ATMs, and medical devices. And the other edition is Windows 10 IoT Mobile, which also supports Universal Windows Platform apps and multi-user support, as well as some lockdown features. And it's mostly aimed at mobile point-of-sale devices and industry handheld terminals. Now, Windows 10 IoT Core was first released by Microsoft publicly released by Microsoft last August 2015. And the last public release was last December. Since then, several Windows Insider Preview builds were released with a lot of improvements, including support for Raspberry Pi 3s. There is very little prior research on Windows 10 IoT Core security, which is understandable since it's still in its infancy. The only research that I'm aware of is the one done by a researcher from FFRI in Japan and was presented at Code Blue 2015. But a lot has changed since then, and this talk will reflect some of those changes. So Windows 10 IoT Core currently supports 4 so-called suggested development boards. First, there's the Raspberry Pi 2 and 3s, which runs on ARM and are 32-bit. And the other one is the middle board Max, which runs on an x86 architecture and also 32-bit. And the last one is Dragon Board 410C, which runs on an ARM processor and also 32-bit. In addition to these suggested devices, Windows 10 IoT Core may also support other devices that is built on the same system on chip or SOC as the above devices. Such for Raspberry Pi, it's a Broadcom system on chip, and for Mino board Max, it's Intel, and for the Dragon board, it's Qualcomm. So even if even if the device is not part of the suggested development boards, you may be able to install Windows 10 IoT Core in it. Also, unless otherwise stated, the OS version that we will be discussing here is the latest Windows 10 preview, which Windows 10 IoT Core preview build, which is version 14.393, and the devices I use are mostly Raspberry Pis and 2s. So first, let's talk about some of the internal workings of Windows 10 IoT Core. But I'm not going to stuff that most people already know, such as the things that are common between this operating system and the desktop Windows 10. So I'm not going into that. I will focus on things that are specific to Windows 10 IoT Core. Windows 10 IoT Core images. First, let's start with the images that use things. Windows 10 IoT Core images uses the Fast Flash Update, or FFU image format, which is also the same format used in Windows Mobile. Windows 10 IoT Core uses the version 2 of this format, and I'm not going to go into detail about this format because there's some documentation from Microsoft, and also there will be a white paper that you can download after the talk, and the links are all in there, so I'm not going to discuss it here. If you want to retrieve the contents of the image, you can use a tool called the Image Mount, IMG-MOUNT, which runs only on Windows, and it will convert the FFU image into a virtual hard drive or VHD image and mount it. So in this example, I'm using Image Mount to convert the motherboard Max FFU file or image, OS image, and when the image mount tool has successfully converted it, it will mount it, and the result is on the image below. So, but if you're not using Windows, there are some alternative tools to do this, like FFU to IMG and FFU to DD, which will both convert the FFU image into a raw image that you can then mount, or you can then use the DD tool to flash it into your SD card. So, but I haven't used these tools much, so your mileage may vary. A Windows 10 IoT Core image contains 4 partitions. So first, the EFI system partition, which is formatted as FAT. It contains the Windows Boot Manager and the boot configuration database. The crash dump partition, it will be mounted to the C directory of the OS in the EFI ESV folder. The crash dump partition will contain crash dumps that were dumped when a crash occurred that caused the device to restart. It's mounted on the D partition, and the main OS partition contains all the components of the OS, such as the registry hives and the system binaries and OEM applications. It is mounted on the C drive. The data partition, on the other hand, is mounted into the U drive, but it is also linked to a folder in the C drive named data, and it contains the installed applications, the user data, and the application data. So next we'll talk about the boot process quickly. This is a high-level illustration of how the boot process works in a Windows 10 IoT Core device. So first, the device powers on and runs the system-on-chip firmware bootloader. And then this bootloader will launch the UEFI environment and the applications, if there's any. And then this UEFI environment will launch the boot manager, which you can find in here in the EFI system partition in the folder EFI/Microsoft boot in the file boot mgfw.efi. This boot manager will then launch the Windows bootloader, which can be found in the system32 folder in the file winload.efi, and the Windows bootloader will then launch the main OS. Next, we'll talk about apps. Windows 10 IoT Core supports different types of applications. First, there are Universal Windows Platform, or UWP apps. UWP is the common app platform used in all Windows 10 editions. It allows the developer to, well, theoretically, develop an app that can run on any Windows 10 versions he may choose to support, with possibly minimal changes in code. So in Windows 10 IoT Core, only one app can run in the foreground, or only one app can be the default app. You can't run multiple apps in the foreground at the same time. You can install several apps on your device, but only one can be set as the default app, and it is launched when the system starts. Another type of application is our background applications, and these are apps that have no UI and runs on the background. So they are launched at device startup and will continue to do so as long as the device is up, and will be respawned whenever they crash. Windows 10 IoT Core also supports non-universal Windows platform apps such as console applications. But in this case, you can only write these console applications in C++, and obviously the Win32 GUI APIs won't be available. Windows 10 IoT Core can also be configured to run on either headed or headless mode. In headed mode, the default app displays a UI, which is fully interactive, and you can use it to control the device. For devices that don't require any user interaction, the headless mode is more appropriate. In headless mode, there is no UI. So if you want to use a device as, for example, a server, you should use the headless mode instead. So now let's talk about the security features implemented in Windows 10 IoT Core. But first let's talk about those features in Windows 10 that are not implemented in Windows 10 IoT. It may be possible that these features may be added in the future, but at the time of writing, these are not supported. So first, it's Windows Defender, which is the Microsoft anti-malware product. There's no Windows Defender in Windows 10 IoT Core. And Microsoft Passport is also not implemented. And the security features that are built on top of virtualization-based security, or VBS, such as Credential Guard, Device Guard, and Hypervisor Code Integrity, are also not supported. Now, the problem with current IoT devices is that they don't usually implement or enable modern exploit mitigations. And the fact that Windows 10 IoT Core implements these gives it an advantage over the other operating systems that are commonly used today. So the executables included by default are compiled with ASLR and DEP enabled. So all the apps that is included and all the system binaries are compiled with ASLR and DEP. But Windows 10 IoT Core currently only supports 32-bit boards, so the ASLR implementation will inherently have lower entropy compared to the 64-bit implementations. It also supports control flow guard, which is also enabled on the installed system binaries, and can be enabled by the developer on their app by setting the /guard :CF switch in the build configuration. Okay, next let's talk about Trusted Platform Module. The Trusted Platform Module is a secure crypto processor that provides cryptographic key creation and storage. Other security features implemented in Windows 10 IoT Core, such as Secure Boot and BitLocker, will only work when TPM is installed. So there are three types of TPMs. First, the firmware TPM, which is TPM implemented in the chip or in the firmware. And the other one is discrete TPM, which is a TPM that's a separate hardware chip module that can be attached to a board. And lastly, there's a software TPM, which is just a software emulated TPM that a developer can use during development. And firmware TPM is enabled in the Dragon Board 410C and Mino Board Max, but it's not available on our Raspberry Pis. So on devices that do not support firmware TPM, you can use discrete TPMs, which can be attached on your chosen board. Software TPM is only an emulation and only provides the software interface for your app, and does not actually provide any security or does not do anything at all. It just allows you to develop your application on a device for the meantime, even if the device doesn't have TPM, but then you can deploy it later on a device that does have TPM without having to change your code. So there are two security features, like I mentioned earlier, that's available for your device if you have TPM installed. One is Secure Boot, which is a feature that prevents a device from being tampered with during boot time, and it stops the system from running binaries that are not digitally signed. It's also designed to protect the system from rootkits, bootkits, and other low-level malware. Another feature is BitLocker, which allows encryption or automatic encryption of the user and system files on the OS drive. So one of the most important problems in IoT security is the device firmware update problem. So vendors usually do not implement automatic update functionality, and updates have to be done manually. And so imagine if you have to manage the updates of lots of devices. A home of the future could have potentially dozens, maybe hundreds of IoT devices installed, and monitoring which devices need updates and doing the update itself would be impossible to manage. So the Windows Update feature solves this problem for devices running Windows 10 IoT Core, as it was added in an insider preview a few months ago or earlier this year. But updates occur automatically and it can't be disabled. Just like I think Windows 10 Home Edition does that too. It updates automatically and you can schedule updates and you can disable it. So, but if you want to do so, there's a Pro Edition of Windows IoT 10 Core, but I think you need a license for that, and that enables you to disable the to have deferred updates. So, and you can check for the updates using the Windows Device Portal that I'm going to discuss later on. The screenshot, there's the screenshot for the update page. So automatic update may be a good idea for most non-tech savvy users, but for power users it would be annoying. In fact, while I was doing this research, I forgot to disconnect my devices from the internet, and they update automatically. And as we know, with the preview builds, sometimes they break stuff. So I had to recover some of the things, and I lost a lot of time doing that, dealing with that. And it happened several times, not just once. Anyway, now let's talk about the attack surface exposed on a device running Windows 10 IoT Core. So in this talk, we'll only be discussing the attack surface exposed on the device or by the OS itself. So it's not that big. The attack surface will be bigger if you factor in the device's connectivity with IoT platforms and services such as Microsoft Azure, and connectivity with other Internet of Things devices through a feature that's built in Windows 10 IoT Core called All Join. However, those are outside the scope of this talk for now, and each of them could warrant their own present talk or paper in itself, so I'm not going to discuss those. Instead, I'm going to focus on the attack surface on the device or on the OS itself. Now, first, let's take a look at the network services that are running on the device. Here's the result of scanning a freshly installed Windows 10 IoT Core device using Nmap. As you can see, SSH is listening on TCP port 22. MSRPC is listening on TCP port 135. MS Directory Services on TCP port 445, and a web server on port 8080. This web server is serving the device's web management interface called Windows Device Portal. In older versions of Windows 10 IoT Core, or the versions that were released last year, there were more ports open by default, and these were discussed by the talk I mentioned earlier by FFRI research in Japan. In those versions, an FTP server was running, and also Visual Studio Remote Debug, which has no authentication, was also running. But in the later versions, they removed that. So let's talk about the Windows Device Portal. Every edition of Windows 10, like a desktop, Xbox, Windows 10 Mobile, HoloLens, and of course the Windows 10 IoT Core provides a web interface that you can use to manage and configure your device remotely. And that web interface is called the Windows Device Portal. It's enabled by default in Windows 10 IoT Core and runs upon device startup. And you can access it by connecting to HTTP, the device IP address, and port 880. The files for the Windows Device Portal can be found in the C drive in the Windows Web Management www on the device itself. So while the Windows Device Portal is useful for device management, it can be a security liability if not configured properly. Why? Because in Windows 10 IoT Core, the default administrator password is hard-coded on the device, and its username, administrator, password, p@ssw0rd. So if you didn't bother to change the default password, your device is susceptible to unauthorized access. So for example, an attacker can use Shodan, for example, to search for devices running an HTTP server on port 8080. That returns a banner containing the string Windows Device Portal, which is returned by Windows Device Portal when you connect to it. That Shodan search will yield a result similar to this. So right now it's just a few machines exposed on the internet. It's probably because most users don't really put it directly into the internet, but inside their own network. But I expect that this will become a lot more in the future. Also, all the operations of the functionality of the Windows Device Portal is built on top of REST APIs, so you can use those APIs to remotely control programmatically your device, and you can also control the devices, several devices at the same time. And I'll show you later how I'm using that. Okay, so on the right side of the screen, you can see the list of all the tabs or the utilities and their functions. But I'm going to take a look. But we're going to take a look at some of the more interesting tabs in the Windows Device Portal. So here's the Home tab. It shows the device information and allows you to change the device name and password, among other things. The Apps tab allows you to install or uninstall an app on the device. It also shows a list of the currently installed applications and their status, whether they're the default app or not, or what kind of apps are those, background applications or not. You can also use this tab to set an app as the default application. Now the Process tab is important. It shows a list of the running processes on the device. It also shows the process owner, session ID, CPU usage, memory usage, and you can also terminate a process by clicking on the X button on the left side of the process ID name. And there's also a box on the top where you can enter a command and have it run on the device as the administrator or as the default account. In the TPM configuration tab, you can select which type of TPM you want to enable. I mentioned earlier there are several TPMs that you can use. In this case, this is a Raspberry Pi device, so you won't see any firmware TPM here. It's all software, and it also lists all the supported discrete TPMs that are supported on the Raspberry Pi. So, depending on the device, you can select from firmware TPMs, various discrete TPMs, and of course, software TPM. As for the other network services that we saw earlier, Windows 10 IoT Core allows remote administration and configuration through SSH, and it's also enabled by default and once upon start. If the user neglected to change the login credentials, an attacker can easily gain access. It can also be susceptible to brute force, password guessing, and brute force attacks. Windows file sharing also starts at boot time, and you only need the IP address of the device and user credentials, the same administrator, default administrator, username, and password to access it. It is also susceptible to default login credential attacks. Now, the Windows IoT remote server is not enabled by default, but you can enable it using the Windows Device Portal. It is a feature that allows the UI, if you're running an application that's headed and not headless, it allows the UI of that application running on the device to be viewed remotely and to be controlled remotely through a client application that you can install from the Windows Store. And that client application can run on mobile phones or desktops or tablets. You can enable the Windows 10 remote server by checking the enable box in the remote tab of the Windows Device Portal. I'm going to show that later. And once enabled, the file nano-rdp server.exe will be executed on the device, and it will start listening in port 8000 for incoming connections. So to use this remote display feature, you need to install the Windows 10 IoT Remote Client app that can be downloaded from the Windows Store. However, this feature does not use any authentication. So anyone who knows the IP address of the device and that device has Windows IoT remote server enabled, you can use it to remotely view the UI and to remotely control the device. Now, another attack surface are device driver vulnerabilities. Device driver vulnerabilities are another potential attack vector on Windows 10 devices, and IoT devices obviously need connectivity with other devices in order to be useful. So to facilitate this, devices would need to use built-in or external peripherals, and these peripherals require device drivers to operate. So these device drivers may contain vulnerabilities that could give an attacker remote access to the device if successfully exploited. So drivers, for example, for wireless adapters such as Wi-Fi, Bluetooth, Z-Wave, and Zigbee are viable targets. One advantage of targeting drivers is that successfully exploiting them will often result in kernel-level privilege. How about malware? Windows 10 IoT Core is as much at risk of malware as your typical IoT device, especially when the owner fails basic configuration. So as we have shown above, login credentials that are hard-coded and are not changed after install makes your device susceptible to attacks. So this is how the majority of current IoT malware typically infect an IoT device, and I think will still be the most common infection method in the years to come. Another possible infection method is the exploitation of vulnerabilities in the network services running on the device. This may not be as common as the login credentials method, but there are malware currently that does this against embedded Linux devices, so it's not an impossibility. But you may think that since these devices are usually inside the home network or some network and are not directly accessible from the outside, you may think that this won't be as much of a problem. But another scenario that this could be exploited is the one that was presented in a paper released, I think, 2 weeks ago by the researchers from University of New South Wales, I think. And they released a paper entitled "Smartphones Attack Smart Homes," and what they basically did was they installed a malicious application on a mobile phone, and then when that mobile phone joins a network, the malware will scan that network for IoT devices that it knows it can exploit. When it has found one, the malware will then use something like UPnP to open the port in the router to make to enable port forwarding in the router to the device, and then inform the attacker or the owner of the malware that it has found a device on that network that it can attack, and then the attacker can now using port forwarding can now attack the device directly, even if it's inside network, another network, a NAT. Another possible way that a Windows 10 IoT device may be compromised by a malware is through lateral infection coming from an already infected machine. There are several ways in which a malware can gain access to a Windows 10 IoT core device on the same network. In this example, I'm coming from a machine that has been used to log in using a remote PowerShell session with a Windows 10 IoT core device. And using Mimikatz, I'm sure you all know what Mimikatz is, which is a popular tool to extract password, hash, pin codes, hashes from memory. And using Mimikatz, I could elevate my privilege and then use the SSP command to scrape LSAS process memory for the login credentials used to log in to the device. In this example, a user has logged in to the administration account on the device with the IP address 10.0.1.108 and using the password Diwata. And Mimikatz was able to get this info from the infected machine's RAM. Another possible scenario would be since by default the Windows Device Portal only has uses basic HTTP basic authentication. One thing that a malware can do is to sniff the network for any activity, any traffic that involves the Windows Device Portal and some machine. And since it can get the credentials from that traffic, it now has the login credentials to that machine and can infect it. Okay, so now let's talk about hacking Windows 10 IoT core devices. First, how do you know if there's the Windows 10 IoT device running on the same network? As it turns out, Windows 10 IoT devices advertise themselves on the network. So this is how the tools, developer tools for the Windows 10 IoT core, such as IoT dashboard, discover devices. So what happens is a multicast datagram is sent to 239.0.0.22 with a multicast port 6. And the data payload of that datagram contains the device name, IP address, MAC address, the BIOS serial, the device type, and the architecture of the device sending out the datagram. So the fixed length data contains the device information, and all strings are in Unicode. And you can use this information to decode the packets, and you can create your own tool that can listen for these datagrams and discover Windows 10 IoT devices running on the same network. One of the most useful built-in features in Windows 10 IoT Core is remote device administration and configuration using PowerShell. However, PowerShell is not just useful for system administration. It's also a powerful tool in security to use in security assessments. In fact, there's a lot of tools written in PowerShell for penetration testing. So there are existing PowerShell modules, both built-in and from third-party developers, that could assist in reversing and penetration testing. Not all of them will work in a Windows 10 IoT Core, but some of those that I have used, that I have verified to work correctly, don't know how to pronounce it, KimSweep, for remotely gathering device information, and autoruns to list auto-run entries. So here's an example of using KimSweep to list auto-start entries. In this case, I wasn't running this on the device itself. I was doing this remotely, so it's good. But alternatively, you can also use autoruns, which can show you more auto-run entries. But however, you can only run it on the device itself, and it doesn't do remote listing of auto-run entries. So there's going to be little difference in reversing a console application compiled for Windows 10 IoT Core versus one compiled for the desktop, but there are some things to take note when reversing Windows apps of Windows 10 or Universal Windows apps. So installed Windows apps can be found in the data partition in the U drive, but it's also linked with the C/data folder, specifically in the Programs Windows Apps folder. App installation folders will contain lists the following: the app's name .exe and the app's name .dll. App name.exe is just a stub that sort of stub that calls the exported function in app_name.dll. And there's also the app manifest and the app and the other stuff. I can't read it. You can see it. The app manifest is similar to the Android XML, the thing in Android, and that it lists the capabilities of the application as well. So other than this files, there are other DLLs that the app uses and an XBF, binary XML files used by the application. There's also an assets folder that contains resources like images and fonts that the app uses. So the app name is simply the app's name.exe file is simply a stub that calls the main exported function in the file app_name.dll. This DLL contains the applications and .NET Framework and third-party library codes. So this is how it looks like. It's just a single function with a call to the exported function in the DLL. So as you can see, it's just calling the app's main code. All Universal Windows Platform binaries are compiled to native code using a technology by Microsoft called .NET Native. And .NET Native is a compilation technology. If you're familiar with Android, there's ART. In that case, your application, when you install your application on the device, ART will compile that application into native code. But the difference is that in .NET Native, your application is compiled in the cloud when you submit it to the Windows Store. So, and when the user is going to install your app, is going to be running on the architecture of your device. One implication of this, just a thought, is that what if you find a vulnerability in the compilation code of the code that converts the IL into the native code? Maybe you'll be able to own Microsoft servers. Just a thought. So the code will be compiled from the same source. So one advantage of this is that you can choose which architecture you're more comfortable with in reversing, and then choose the version of the binary compile for that architecture by installing it on the devices that runs on that architecture. So another thing to consider is that while we can deal with code written in C++ as reversers, like we've always done, if the code was written originally in C# or maybe Visual Basic, it would be different. You would have to handle it differently. Binaries in .NET languages are compiled into intermediate language code, and we can usually decompile them using .NET decompilers such as ILSpy or .NET or Reflector. But with UWP apps, they are now compiled into native code, so we can't use those decompilers anymore. And we have to deal, and the result is we have to deal with idiosyncrasies in the resulting native code due to the conversion being done. But that's another topic, and maybe someone will do a talk on that, reversing UWP apps. I want to see that. So let's talk about kernel debugging. To dynamically reverse kernel level code such as device drivers, we need to do kernel debugging and using WinDebug. Here I'm using a Shikra connected to a Raspberry Pi, and I'm connecting the TX pin of the Shikra to the RX pin of the Raspberry Pi, and the RX pin of the Raspberry Pi of the Shikra to the TX pin of the Raspberry Pi. So one thing I want to stress this is that when I first do this for some other devices, I was connecting the TX to the pin to the device's TX pin, and the RX pin from the Shikra to the device's RX Shikra, and I didn't know that I was doing it wrong, and I wasted several hours on that. So hopefully you don't do the same mistake. Next, you connect your device using PowerShell or SSH. You will then need to enable serial debugging using the serial debugging and turn on the debugging with the following commands that you see on the screen. You can find out the COM port used by your USB to serial adapter by looking at by using the device manager or the GUI in Windows, the device manager. Or you can, it's a much easier method, or is running the following PowerShell command. So in the example, my USB to serial adapter uses COM3. So you can now, after this is after you have retrieved the COM port number, you can now remotely debug the device on your machine by running the following commands. And make sure you're using the x86 version of WinDebug, because you are debugging an x86 processor. So if all goes well, you will see WinDebug spawned like that, and waiting for the kernel debugger to connect. And what you have to do next is simply restart your device, and you're good to go. So for user mode debugging, it's a bit easier than kernel mode debugging. You don't have to use USB to serial device. You only need a network connection to your device. So here we are going to use the debug server.exe, which can be found in the device's Windows on the C drive, Windows System 32 debuggers folder, and you only need WinDebug on the debugging host machine. First, we need to make debug serve.exe listen on a port on the device, so we can connect to it. Any port will do as long as it's not being used. On the device, you can run that command, and once you've done that, once you're sure that there's no problem, you can open WinDebug running on the debugging host or in your development machine. Go to File, Connect to Remote Stub, and then enter the IP address of your device and your chosen port in the format shown in the screen. Then click OK. After that, you'll see the dialog box in the right come up, and you go to File. You first go to File, Attach to a Process, and then you'll see that box, and then you select the process you want to attach to. So if the process attachment was successful, you'll see the debugger, and from here on, you can do whatever you want. So I said, Crash dumps can also be found in the crash dump folder, and you can use WinDebug to debug the crash dumps. So I'm going to rush. So in this example, I downloaded a live process dump of webmanagement.exe, and you can use WinDebug to debug it. Lastly, this is fuzzing. Fuzzing is one of the most effective ways in fighting vulnerabilities in software, so it's no brainer to attempt this in Windows 10 IoT Core as well. Unfortunately, due to the lack of existing tools for this, the approach we have been doing so far is far from efficient. It do spawning processes using debugger, and there's no coverage measurement, and some of the steps are manual. But in this picture is my Raspberry Pis. I call it my lackluster fuzz cluster because it looks disorganized. So I'm using the REST APIs in the Windows Device Portal to control process start, process stop, and the collection of crash dumps. So all of this is not really sophisticated, and it's basically fuzzing like it's 2007. And also the device slope CPU power severely limits the rate of fuzzing iterations we can do. So one interesting approach would be corpus-driven fuzzing, because here you can take an app and fuzz the desktop version of the app, and then collect the samples that have very good coverage. And then once you collected it, you then pass it on to the IoT version of the app, and you don't have to instrument it on the app itself. I'm sorry, I'm losing time, so I'm going to rush. But this approach will be applicable if you want to fuzz drivers for peripherals, because or for fuzzing applications that interact with hardware. In those cases, you have to do on-device fuzzing. However, there were surprising developments recently, like the release of WinAFL, and this is currently an ongoing project of mine to make it work on Windows 10 IoT devices. Hopefully, I will have something to show for that in the near future. So, recommendations. We have gone through how Windows 10 operates, and now let's summarize the various ways we can minimize the risk against these devices. First, segment your network. Segregating your IoT devices from your traditional computing devices, such as laptops, is highly recommended. Also, protect your network services. Use the built-in firewall. There's a built-in firewall in Windows 10 IoT, and don't disable the services that you don't use. Also, obviously, you have to change the default administration password. You can pretty much eliminate the low-hanging malware infections on IoT devices by doing that. Also, use TPM. If you're doing a hobby project, it's fine not to use one. But if you're going to do something sensitive, in sensitive situations as home security, you should be using boards that support TPM. And then you should take advantage of the available security features, such as Secure Boot and BitLocker. So now it's time to wrap up the talk. Windows 10 IoT Core is still in its early stage, but I believe that once it matures, it will become a more viable alternative to the other IoT-focused operating systems that currently exist. Aside from the many features the OS offers, including security features that we've discussed, what makes this OS attractive is that there are a lot of enterprises and developers that have already invested in Microsoft technologies, and they can leverage the knowledge and the expertise that they already have in developing the IoT devices of the future. So this would also mean that this OS will be a more attractive target for attackers, although the attack surface that we discussed today is smaller than other computing devices. If you factor in IoT services, platforms, and interconnectivity with other devices, that attack surface will definitely be bigger. So to mitigate the risk against this attack surface, vendors and makers should be more wary about misconfigurations that the attackers may take advantage of. So, and lastly, it is my hope that to counter the potential attacks on Windows 10 IoT Core devices, more people will engage in security research aimed at this OS, and that this talk has somehow helped encourage it. So that's it for my talk. Thank you all for listening. If you have any questions, there's still a minute left, I think. But if, yeah. Huh? 20 seconds. Okay, you can just approach me after this if you have any questions. Thank you. Thank you very much.